In this problem, we are going to take a look at a homogeneous real-world model. Typically, these are called equilibrium pricing models, and it involves a series of industries, the goal of which is to figure out how much they should price things at in order to keep the system in equilibrium state. So that basically means that we want to make each sector's income match its expenditures. Well, let's go ahead and read through this. Suppose an economy consists of coal, electric, and steel sectors, and the output of each sector is distributed among the various sectors as shown in Table 1. Okay, so each of these economies is going to have some output. We'll call that output 100%, and a certain proportion of that is going to be distributed just among those three sectors. So we'll take a look at this table here. In this table, we'll see that coal distributes its output in the following ways. It doesn't hang on to any of the coal. It distributes 60% of its coal to the electric sector and 40% to the steel sector. For electric, we can see electric sector is divided as follows. 40% of what they produce goes to coal, 50% goes to steel, and the remaining 10% to electric. So how do we envision that? Well, electric treats this 10% as an expense. It occurs in order to operate its business. Since all output must be taken into account, the decimal fractions in each column must sum to 1. So we can observe these all sum to 1 going this way. Not necessarily across the rows, because, well, that's just the output that the company is buying. So they could buy, 40%, they could buy even 100% of all three of these per sector. So we see that these may not sum to 1 going across the rows. But down the column, we're accounting for 100% of each sector's production. Denote the prices of the total annual outputs of these three sectors by X, Y, and Z respectively. If possible, find equilibrium prices that make each sector's income match its expenditures. So the constraints that we're dealing with here, and I'll just write them generally because there's going to be three sets of constraints, one for coal, one for electric, one for steel. We want to make sure that income equals expenditures. So for example, if coal, let's say, just as an example, let's say X is equal to 100. Okay, so what does that mean? Well, that means $100 of coal produced. So I always like with real world models to try to make sense of what is happening first. And in this case, the reason I'm starting with X equals 100, because that tells me how much is going to be purchased by electric. So that means electric purchases, well, they purchase 60% of the 100. So they are going to spend $60 on coal. We do the same thing for coal purchases, or I guess we should say coal's expenditure on coal is 0% of that 100. So basically they do not have, oops, that should be $0. Let's try that again. And then the remaining $40 is going to be purchased by steel. Steel purchases 40% of the 100, which is $40. And so that sums to the $100, as it should, because these percentages, these proportions add up to 100%. Okay, the reason we mention that is because notice that the total amount purchased by these three sectors is 0% of X, 0.6 of X, and 0.4 of X. So if I take this and treat this as a vector of 0, 0.6, and 0.4, then the amount purchased by the three sectors will be X times that, right? It's, in other words, what proportion of the X dollars are each of these three industries purchasing? We can do the same thing for the total production of electric, which is represented by Y, and that would be in dollars. So if they produce $100, then 40 would be purchased by coal, 10% would be purchased by electric, and 50% would be purchased by steel. So it would look like this: 0.4, 0.1, and 0.5. And then we similarly would have for steel, we'd have Z. That would again be how many dollars of output steel produces. And then 60% of that dollar output goes to coal, 20% to electric, and 20% to steel. So each of these vectors represents the dollar amount, in this case, of coal purchased by each of the three sectors. Okay, so this is the expenditure, in other words. By coal, right? That's how much or I shouldn't say expenditure by coal. These represent the expenditures of the three sectors for coal. Now, because we know that the top row represents everything that coal will buy, the middle row represents everything that electric will buy, and steel represents everything that, or the third row represents everything that steel will buy. If we add these three things together, well, that's going to, the sum of these will represent all of the purchases by each of the three sectors. And so if you write it out this way, if you want to write it out as a system of equations, 0x plus 0.4y plus 0.6z, we don't have an equation, I should say expression, 0.6x plus 0.1y plus 0.2z. Again, that middle row is the total expenditures by electric, and then the bottom row, 0.4 of x plus they'll buy 0.5 of y, plus they'll have expenditures of their own. And these expenditures, what do they need to equal? Well, they need to equal the total amount of income, right? So I guess we have our setup as expenditures equals income. Well, how much income do each of these three sectors get? All right, so this is going to be the income. Well, that is exactly what the variables represent. They are going to sell 100% of what they produce. So coal is going to make X dollars of income, right? Because if X is 100, that they're going to sell it all. They're going to sell all $100 of it among the three. Well, some of it will be kept, right? And that's what the 0x is accounting for over here. And also then the electric sector will produce Y dollars. That'll be their income because they'll sell it all 100% of it gets sold. And then the steel sector will produce Z dollars of steel, and that will be their income. So if we put these values in here in the system of equations, well, notice that an interesting thing happens here, and that is that these three terms represent the fact that there is some internal expenditure by each of these three sectors. Not so much for coal, right? Because when we move that X over before we solve this system, we would subtract 1x, 1y, 1z, and this would give us negative 1x plus 0.4y plus 0.6z equals 0. Because remember, on the right-hand side, we need our constants. Right now, we have variables on the right, so we have to rearrange things. In the second equation, 0.6x minus 0.9y, right? So that actually tells us that they have a negative expenditure, which means they're actually making money. They're basically hanging or making 90% of what they produce, because 10% of it is internal expenditures. So the other 90% is what they make on it. Plus 0.2z equals 0. And similarly, if 20% of steel represents an internal expenditure, then that means 80% of what they produce gets sold, and that's why we'll see this plus minus 0.8z. The reason you can think of them as being negative is because this represents expenditure on the left-hand side. So having a negative expenditure actually means you're making that money. If that bothers you, multiply both sides by a -1, and then the revenue, or the income will be positive and the expenditures will be negative. So just which side things are being moved to is our explanation for why this happens. And then we have minus 0.8z equals 0, and 0.4x plus 0.5y. Now, since we have our system set up now we can produce our matrix: -1, 0.4, 0.6, and 0, 0.6, -0.9, 0.2, and 0, 0.4, 0.5, -0.8, and 0. And now we're going to reduce the system. Notice this is a homogeneous system. So it will have either one of two things. It's possible that the only solution is 0, 0, 0, or two, there would be then infinitely many solutions. Why is that? Well, because 0, 0, 0, or basically in this case, because we have three variables, 0, 0, 0, would be a solution to every three variable homogeneous system. So you know there's at least one. The only other possibility is that if there's more than one, well, that would mean that there's infinitely many, but there's always going to be at least one. So there are two possibilities for what can happen. And when we reduce this, I'll go ahead and write this down, we get this following matrix right here. And let's begin to analyze the solution set. As we can see, the bottom row doesn't give us any information. 0 equals 0, true statement. So bump up to the next row. Well, let's start at the top now. Notice we have a non-zero pivot here. That means x is not a free variable. Go to the second row, we have a non-zero pivot here. That means y is not a free variable. Remember, the reason we're saying those aren't free is because it's much easier to isolate x and y in these two rows than it is to try to isolate z. And also notice that there's no more leading ones in this matrix. We're out of rows, and that means z is free. And the other way you could imagine that is because notice that x and y both depend upon z. So we'll say something like this. We'll say let z equal some real number c. And what we're doing here is we're just saying z is a continuum of values from -infinity to infinity. So let's assign it some number. So that c is just some number. And then that would mean that our solution set, x, y, z, would be, well, let's see here. We would have 0 plus 0.94c, right? Because if x plus or minus 0.94c equals 0, then x equals positive 0.94c. Y equals 0.85 of c, whatever that z value we give it, and then z equals c. And if we wanted to write this in parameterized form, we could just see that any multiple of the vector 0.94, 0.85, 1 is a solution to this system. So how do we then go about interpreting this? Well, we could say that basically for any constant c, even 0, not a very interesting solution, right? They could all just produce nothing, and that would leave them in equilibrium because their incomes would be 0, their expenditures would be 0. But more importantly, this suggests that the number of dollars of production, you'd have to say something like this. You could say for every $1 output of steel, there needs to be 94 cents of coal produced and 85 cents of electricity. And for what? For what? Well, to keep equilibrium prices. So In other words, if C was 100, then you would need $100 of steel, $85 of electric, and $94 of coal. And that would ensure that the income, the expenditures, based on the distribution of these percentages that are going to be spent by the three sectors. So that's what we're saying here, and that's why it helps to see this in parameterized form, because it just gives me a ratio that must take place among the three components. And it's nice because we can describe it in terms of $1 of output. And then really, if we wanted to produce $1 million of steel, then we need $850,000 and $940,000 of electric and coal, respectively.